Assalamu alaikum students. Welcome to our third lab session for the course Digital Logic Design. My name is Ali Roman and this session is specifically designed for the students of BCS 3A. So in this lab basically we will be implementing the full ladder circuit using verilog HCL and by using model sim tool in order to simulate and in order to perform functional simulations. So the today's session is based on three major parts. First part is the introduction. The second part is the theoretical background of adders, and in which we will be discussing the basic full adder circuits and the Boolean functions associated with that full adder circuits and how the addition of three binary bits are performed. And at the end, we will be having the demo regarding the particular session. As far as the reference readings and acknowledgements are concerned, we are at chapter number 3 and chapter number 4 of the book Digital Design with Introduction to Verilog HCL. In our previous session, we have implemented the half adder circuit that has the capability to add two binary bits and produce the result in terms of sum and carry, whereas the full adder circuit is a circuit that has the capability to generate arithmetic sum of 3 bits. So this is the major difference between half adder and the full adder circuit. Half adder can perform only half addition, but at any particular possible case we can have any possibility of adding 3 binary bits. For example, let us assume that we are adding two numbers. For example, we are adding 1 0 1 1 with 1 1 0 1. As far as the first addition is concerned, we can perform this first addition at the least significant position by using half adder. So 1 plus 1 equals 0 with 1 carry. Now as far as the next consecutive addition of these three binary bits, the half adder doesn't have that capability to add these three binary bits. So we do need a circuit that has the capability to add three binary bits together. So we will add 1 with 1 and then 0. So 1 plus 1 equals 1 0, so and plus 0 equals 0 with 1 carry and so on and so forth. So the full adder circuit basically is a circuit that has the capability to generate the arithmetic sum of three binary bits. So as far as the addition of n binary bits are concerned, we require to use n full adders. So if we have to add the two numbers of n bits each, we require n full adders, in which we use a mechanism that the carry out of one adder is forwarded to the next consecutive full adder for the next addition. So the process of addition proceeds on a bit by bit basis, right to left, beginning with the least significant bit. So here what we are referring from the right side is basically the least significant bit. So we will add basically in that particular case we start addition from the least significant side and we move towards the most significant side. So after the least significant bit addition, at each position add not only the respective bits of the word but also consider a possible carry bit from addition at the previous position. For example, in this particular case, this carry basically is being generated with the addition at the previous position, that is this particular position. So this is a circuit that has the three bit input, or you can say that three dedicated inputs for the three bits, and we've got two dedicated outputs, one for the sum and one for the carry. Now if you see the truth table and the boolean functions of the full adder, this is basically table 4.4. what we are doing that x, y and z are the inputs and c and s are the outputs. C represents the carry out and s represents the summation operation. So we are adding x plus y plus z basically. So 0 is added with 0, then it's added with 0, sum bit is also 0 and carry bit is also 0. But for the case here, but for the last case, if 1 is added with 1, this is 1 0, the 1 is carry that is being produced, and 0 is added with 1, it's again 1. So sum bit is 1 and carry bit is also 1 in this particular case. So if you see the maps for the full adder circuit, we can see that we can simplify the carry expression, that is basically xy or xc or yz. We've got three dedicated pairs with these elements is the shared element between these three pairs, and we've got three terms extracted from these different pairs. Whereas as far as the sum is concerned, we cannot form any pair in diagonal, so that all the four terms are appearing in the statement. But we can reshape this statement, or we can reshape it into another form by using Boolean algebra. For example, if we take x prime common from these two terms, we got y prime z plus yz prime, and if we take x from these two terms, we got y prime z prime plus y prime plus y and z, or y and z. And then for the further simplification, we can see that we are converting this into the two exclusive OR operation. So we can represent this expression as, that is x exclusive OR y exclusive OR z. And similar is the case for the carry. We can also convert that the base carry expression or the Boolean function without simplification into the form. We can represent it as x exclusive OR y into z or yz, or we can say that xy. Let me rephrase it as xy. Already this term is already generated here, so we don't have to reuse that while implementing that. So as far as the logic diagrams are concerned, this is the logic diagram for the sum expression. We've got four minterms here. These are the four minterms, and we are performing the OR operation here. And as far as the carry out is concerned, this logic diagram basically represents the carry out expression with three product terms and one OR term. So in order to implement the full adder, we can implement the full adder by using the half adders and the OR gates. So this is basically the objective of today's lab. We have to implement a full adder circuit by using the half adder circuit, which we have designed previously in our previous lab. So we can see from the expression of sum here that sum can be represented as z exclusive or x exclusive or y. And we can say that here from these two terms we have taken z prime common, and from these two terms we have taken z common, and we have seen that these terms are basically, these four terms are converging or to have this having this equivalent form of this thing. So we can use two exclusive OR gates in order to implement some expression instead of using four AND gates and some OR gates and some inverters. As far as the carry is concerned, this is basically the same term x exclusive OR y into z plus xy. This is basically the same term which is appearing before in our previous slide. Well student, this is the logic diagram of the implementation of full adder by using the half adders. So in this particular case, we are utilizing the concept of the previous lab because we have implemented half adder previously. What we have to do is we have to instantiate that module in our full adder module, and we will have to perform the interconnection so that we can implement a full adder circuit. So if we see that this setup is our first half adder, and this is our second half adder, and with addition of one additional OR gate, we can perform the full adder operation by using two half adder and one OR gate. Now let us go to the demonstration. What we have to implement, basically we have to implement the full adder circuit by using the half adder circuits. But now for the demonstration, this is basically your task. You have to implement that full adder by using half adders. Right now what I am doing is I am implementing the full adders basic expressions, or we can say that the boolean functions, so that we will simulate our design and we will see how the addition of 3 binary bits are performed. So let us go to the software model sim here. So I am closing all the previous projects and I am creating a new project. This is basically our lab 3, and the location of this folder is, I am creating a new folder in C drive with the name lab 3 and selecting that folder and pressing OK. Now the location of the project is C:/lab3. The default library name is work, and I am copying the library mappings in my project. Now what we have to do is we have to add the files which are previously created. What you have to do is you have to just add the half adder module file in your project that you have previously created in your lab. But now for the demo I am basically creating the new files here. So one is the full adder, changing the file type to verilog because we are working in a verilog platform, and I am creating another new file that is testbench or t_full adder, and changing the file type to verilog and pressing OK and closing this tab or window. Now going to the full adder module, we have to define the module. So I start with the keyword module with its name and the port list. So let us assume that we've got the inputs of A, or we can say that in our previous case X, Y, Z, and the outputs are S and C out, semicolon. X, Y, and Z are the pins that I will use for the inputs, and S and C out are the pins that I will use for the output. And I'm gonna end this module with end module keyword. Now what I have to do is basically I have to identify the inputs and outputs. So with the keyword input, we've got X, Y, and Z. These are the inputs, and outputs S, C out. And if we have to define some wires here, we will gonna define our wires here. So wire, I am just randomly right now defining the wires, but what you have to do is first of all make the logic diagram, properly label your wires so that you know the requirements, that how many wires are is required in order to implement the design. So I am just describing my design. Let us see how many wires we can use. So I'm naming the wire as W1 and W2. I hope so these are sufficient enough, but we can introduce more wires if the hardware requires some more wires. Now we know that the sum expression is basically A exclusive or B exclusive or C. So either we can implement a one exclusive OR gate, exclusive or by exclusive OR A, B and C, but for the carry out expression we do require exclusive OR B. So what I am doing is I am separately implementing those both exclusive OR. So first XOR gate, XOR is first instance, and the output is, for example, W1, and the inputs are X and Y, semicolon, and the next XOR gate, XOR the second instance of that exclusive OR gate, and the outputs are S, comma, W1, comma, Z. So this is our sum expression that is being computed, or that is being described here. For carry out expression, first of all we use the two AND gates. So AND instance 1. The first AND gate will produce the AND expression of X exclusive OR Y with Z. So let me name it as W2, comma, W1, comma, Z. The second AND gate basically produces the term that is X into Y. And let me define another wire. For example, here we require another wire, W3. So here we've got W3, comma, X, comma, Y, semicolon, and the final term, that is the OR term, or instance 1, and our result is basically Cout now, Cout, comma, W2, comma, W3, bracket is closed, and semicolon. So this is the total description of our flow ladder. We're going to save this file, and we're going to see if there exists some syntax error or some any sort of error which we have done. So our compilation is basically successful. Now for the second part, what we have to do is, in order to test that, we have to design a test bench. So I am opening this test bench module file. So I am going to define module T underscore flow ladder and semicolon. Then what we have to define is, we have to define the inputs as reg X, comma, Y, comma, Z, and we have to define wire to our outputs, wire space S, comma, C out, and semicolon. Now the next step is, we have to instantiate our design or module which is going to be tested in this test bench. So our module name was flow ladder. Its first instance X comma y, comma z, comma s, comma C out, and closing the bracket and placing semicolon. Now the module is instantiated. Now the next step is to provide the combinations of input for which we have to test our design. So we have to use, first of all, let me end it with AND module. Now what I have to do is we have to use an initial block starting with begin and end of the initial block. So for the first case, x is equal to 1 tick b 0, y is equals to also 1 tick b 0, and z is also 1 tick b 0. So this is the first combination for which I want to test my design. Now using the software delay of 200 time frames, I am basically replicating the inputs and changing its values. Here I am setting the z equals to 1, and I am repeating this for the rest of the combination. This is 1, this is 0, and for example I am just testing another combination. In which all the bits are, or all the inputs are 1. So what students you have to do is you have to modify this test bench file, and you're going to test all the possible combination of inputs, so in order to verify your design. Just saving this file. So this is my test driver circuit that is ready now. I am saving this file, and let us see if we've committed some error, some syntax error. Now all the files are successful in compilation. Now the next step is, this is our main module, this is our test bench. Now the next step is we have to simulate our design. So before simulating, let me complete this test bench for you. Now all the combinations are completed, and we have to save this file, and I'm going to compile this file again, compiling all the files. So no errors, compilation is successful. Now the next step is to simulate our design. We'll go to simulate option and we'll start our simulation. Go into the work folder and selecting that test bench file or the instance and pressing OK. And adding all the components to the waveform here. See, we've got X, Y, Z, these three are inputs, and S and C out, these are the outputs. S for the sum and C out for the carry out. And now we're going to run our simulation. To see here, if x is equal to 0, y equals to 0, z equals to 0, s is also 0, and c out is also 0. If x is equal to 0, y equals to 0, z equals to 1, summation bit is 1 and carry out is 0. For the next combination, x is equal to 0, y equals to 1, z equals to 0, sum is 1 and carry is 0. For the next combination, if x is equal to 0, y equals to 1, z equals to 1, now sum bit is 0 and carry is 1. Similar is the case for the last possible combination here. See here, x is 1, y is 1 and z is 1, the sum bit is also 1 and carry out is also 1. So our full adder is operating properly, and we have designed the full adder circuit that is adding 3 bits correctly. So student, what you have to do is, first of all, let me end the simulation. What you have to do is, you have to design this full adder module by using the half adder modules which you have designed previously. So instead of using this, you are required to use the half adder modules. You are going to instantiate those half adder modules in this file 2 times and use your interconnections in order to interconnect those, and additional OR gate in order to produce the carry out expression. The change in the full adder test bench is not required. You will use the same test bench in order to test your design. Well student, this is all for today's lab session. I hope so you've got the idea of how you will implement the full adder circuit using Verilog HTL in model sim and going to simulate in order to perform the timing simulations and functional simulations. Here in this particular case we are performing functional simulations. We are not performing timing simulations here because we are not taking the real timing delays that are incorporated in the hardware. Okay students, if you got any query or any problem, we can address those queries in your lab sessions. Till now, Allah.